You may have heard of the P versus NP debate. Just to quickly remind you, P is the class of problems that can be solved in polynomial time, whereas NP is the class of problems that can be verified in polynomial time. And remember that P is a subset of NP. The P versus NP problem is asking, are these sets P and NP equal or are they not equal? And the implications of this are pretty important for the world of computing. So first of all, let's think of our four classes of computational complexity with respect to either of those scenarios, either P equals NP or P does not equal NP. If P does not equal NP, that would mean that NP is some set of problems. P is a subset of that set. We knew that in advance. So these would be the problems that can be solved in polynomial time. And then everything that's within NP, but not inside P, would be the set of all problems that can be verified in polynomial time, but not solved in polynomial time. There would exist problems that cannot be solved in polynomial time, but can be verified in polynomial time. And then NP hard is any problem that's at least as hard as the hardest problem in NP. And then NP complete is the intersection of NP and NP hard. So it is the hardest problems of NP. If P equals NP, so in other words, if every single problem that can be verified in polynomial time can also be solved in polynomial time, that would mean that NP is a set of problems that can be verified in polynomial time, and P equals NP, so every single problem in this space can definitely also be solved in polynomial time. And by definition, because it's the intersection of NP and NP hard, it's also equal to NP complete. And then NP hard consists of any problem in NP or anything harder than NP. So it's the problems that are at least as hard or harder than the hardest problem. So at least as hard as the hardest problem in NP. So which of these two scenarios is it? Computer scientists and mathematicians have been debating this for quite a while, but we don't know. The current state of affairs is that it seems likely that this is the case because so many people have tried to prove it, to prove that P equals NP, and it doesn't seem like there's a clear proof, and many problems that can be verified in NP, a lot of people have not been able to come up with solutions to those. So the current state of affairs is that it seems like P does not equal NP, but we don't know for sure. What does this distinction have as far as larger impact? Well, if P does not equal NP, that means that some problems that are actually very difficult, maybe there actually is not a solution to them. Maybe not only have we not found a solution, but no solution exists. That has different implications in different fields. So for example, in the world of biomedicine, protein structure can give you a lot of insight into potential therapeutics, but this protein folding problem is a very hard problem that we don't know if there's a solution. So if we could solve that problem efficiently, that would have great medical implications. However, a lot of cryptography and encryption depends on the notion that I can encrypt a given piece of data in some way, and the computational problem to decrypt that data is sufficiently challenging enough. There is no efficient solution such that my data are safe. So if P equals NP, that would have good implications for certain biomedical problems and various other problems that we would like to be able to solve, but it would have very bad implications for security. So it's kind of this tightrope. It's not clear which of these scenarios we should want, but regardless, we don't know what the current state of affairs are. Again, we think this seems more likely, but we just don't know.